Hi guys, welcome back to my channel. Today we're going to be doing a brief introduction to confidence intervals, and I'm going to show you how we can use them to estimate the population mean from a set of samples. Previously we've looked at the central limit theorem. The central limit theorem tells us that the average of a set of sample means is the same as the population mean. So what I mean by that is if I was to take some samples, so let's say I'm looking at the length of time of a TV show, and I have 10 different shows that I'm examining, and I'm going to take 10 different samples for each length of this show. From that, I then went ahead and I calculated the means of each of those samples. Once I did that, I compared that to the overall average, and I found that those two values were the same. So you can see here, depending on what we're looking at, so if I was to take the average of the sample means, that's this value here. If I was to take the average of the individual shows instead, the average of those averages is again the same. And if I was going to take the average of the entire population, then indeed that also works out to be the same value. So that's a really cool thing about populations and their sample means. However, if you examine the individual sample means, so just looking at these boxes here in yellow, then you can see that they're only going to be approximate to the population mean. Let's use the same example. So we've got a population of 100 different values, and these are all different lengths of different TV shows. So what we could do is we could take the entire population and we could find the average of the entire population. And this is something that seems fairly feasible when we only have a sample size of 100. But what if we were to increase that? What if that suddenly became really, really large? Let's say we had a population of 1 million. It seems a little bit less feasible to actually do that now. So what we're going to do is we're going to take a sample, and generally we should have samples equal to about the square root of the population. And so let's say I calculate the means of each of those samples, and I have a mean of 43.8. Let's do a mean of 67.2, and then my last mean of 33.66. So what would happen if I was to take a whole bunch more of these little samples, and then I was going to draw a distribution of what those means look like? What would that distribution of the sample means actually turn into? Assuming the underlying populations is normally distributed, so the movie show length is normally distributed around a certain mean, and we had determined that that mean was equal to 48.22. Then the sample means will also be normally distributed. And again, if I was to take lots of different samples, then this sample mean would also be equal to 48.22, as we saw above. But what we can see here, as we pick different values, and again, these values are randomly selected, so we're randomly selecting 10 values from this sample here, and we're calculating their mean. So the chances of pulling 10 values from this extreme end are very unlikely. Similarly, it's also very unlikely to get 10 samples that are all situated around the opposite end or the opposite extreme here. And so what we start to see is this tightening up of the sample means distribution compared to the population distribution. So the deviation around the average sample means is much tighter compared to the population deviation. Really what we want to know is that if we were to take a sample mean, how close would that be to the actual mean of the population? Let's say that we wanted to find out what is the probability that our sample mean is 2 standard deviations within the population mean. So looking at our normal distribution here, what we can see is that if we were looking between 2 standard deviations within the mean, we know that's going to be equal to the area under the curve between these 2 points. Now, if we have a standardized deviation, which we do, then we can use the z-scores. And we know that at negative 2 standard deviations from the mean, that our z-score is going to be equal to negative 1.96. While if we were looking at positive 2 standard deviations above the mean, then what we would be looking at would be z is equal to positive 1.96. So really what I'm looking for is the probability that it falls between negative 1.96 and positive 1.96, which is about a 95% probability. So there's a 95% probability that the sample mean is within 2 standard deviations of the population mean. So very, very carefully, just listen to this. This also means that there is a 95% probability that your population mean, so your actual mean, is within 2 standard deviations of the sample means. So that means that you can be 95% certain that your sample mean is similar to the total population mean. This is called a confidence interval, and we can use it to estimate the population mean from a sample. We can do that using this formula, where the sample mean plus or minus ZS over the square root of n, where x is equal to the sample mean, s is equal to the sample standard deviation, and n is equal to sample size. So I'm going to show you a quick example here. After surveying 20 people in your class, you find that they plan to spend an average of $4.53 on their lunch today. The standard deviation for your sample was 23 cents. Use the statistics to state a 95% confidence interval for the average amount that will be spent on lunch today. I've gone ahead and written down the key statistics. So I've decided to use the sample mean because I'm looking at a sample of classmates. I'm not looking at the entire school. That means I'm also going to use the sample standard deviation. So a 95% confidence interval will have a z-score of 1.96. So substituting each of those values into my formula, I can get an upper and a lower limit. So here we have 4.53 plus or minus 1.96 multiplied by 0.23 over the square root of 20. So simplifying, this becomes 4.53 plus or minus 0.10. So firstly, I'm going to find the lower bound. So that's going to be 4.53 minus 0.1, which is equal to 4.43. So that's my lower bound. I'm going to go ahead and find my upper bound limit now. So that's going to be 4.53 plus 0.1, which is equal to 4.63. So I have a 95% confidence interval between 4.43 and 4.63. So what this means is if I was to sample my classmates, so I was going to pick out 20 classmates and I was going to do a random sample each time, there'd be a 95% chance that the mean would fall between 4.43 and 4.63. And this would be close to our mean of 4.53, and so we could say with 95% confidence that our mean is going to lie within that range. Alright guys, so that is a brief introduction to confidence intervals and how we can use confidence intervals to make guesses or assumptions about the closeness of a sample mean to an actual population mean. Alright guys, I'll see you in the next video.